As I said, on your calculator you've actually got two log buttons. And the other log button here. So I'll say this. Logarithms, let me put these back the other way. Logarithms to the base 10 are called common logs. And your calculator has a log button on it usually that says log. But it turns out there's another base that is used quite regularly, and it's logarithms to the base to the number of e. Now, I don't know if you've come across the number e before, but here, so aside, let me just write this. E is Euler's number. Euler's number. E for Euler. And it is irrational. It's like pi. It is irrational. So its decimal approximation, or its decimal representation, goes on forever with no repeating pattern. And it's about, the actual value is about 2.718, etc., etc. It goes on like that. And it turns out that for a lot of applications, E is the best base to use, and hence it's called a natural logarithm. And you will find out why that is the natural base to use when you come to calculus. When you get to calculus, all your formulas turn out to be easier if you use E rather than any other base. Okay? It turns out that with logarithms you can use any base you feel like. We can swap quite happily from one base to another, and as a result we have a tendency always to swap the base E. And on your calculator, your natural log is represented by the ln x. I have had students calling it the in button, but it's not. It's actually ln. It's probably a lowercase l they're using there. But the ln button is your log to the base e. It's the natural logarithm. So ln x is equivalent to log to the base e x in there. So you should have a look on your calculator and make sure you can find the log, the natural log button sitting there. So let's evaluate these things here now. So the log to the base e, the natural log of e cubed, says, what power must e be raised to give e cubed? 3. So I didn't need to do anything there other than understand what the notation meant. B says, what power must 10 be raised to give E? And the answer is, I have no idea, but my calculator knows it. And so via my calculator I'll say this is approximately 0.434 to 3 decimal places. Again, that's via a calculator. 0.434 seems reasonable, because we said back here the log of 3 was 0.477. 3 is just a little bit bigger than 2.7182, the decimal approximation of E. So this power should be just a little bit greater than what we got for the log of E. So I say my common sense tells me this seems like a reasonable answer in here. The last one says go the other way. log 10, the natural log, is the log to the base e of 10. So it says, what power must e be raised to give 10? And again, I can't do that in my head because I'm not very good at such things, but the calculator gives us 2.303 to 3 decimal places. So i.e. e to the 2.303 is approximately 10. And I guess in this one I should have said i.e. 10 to the 0.434 is approximately E. So that's the idea of a logarithm. We'll probably revisit a lot of this stuff, but for the minute, let me just quickly now sketch the graph of a logarithmic function in here. So let me just quickly go through those features that we talked about before. What's the domain? In this case, the domain will be the set of x values where x is positive. I can only find the logarithm of a positive number when the base is 10. So I'm only going to have a graph on the right half of the plane. The y-intercept. Well, there won't be a y-intercept because the function isn't even defined at x equal to 0. So there is none, no y-intercept. X-intercept. Where does log equal to 0? Well, look, I know that 10 to the 0 is equal to 1. That tells me that the log of 1 to the base 10 says, what power must 10 be raised to give 1? Is 0. So when is my function equal to 0? When x is equal to 1. So it actually cuts the x-axis down there at 1, 0. That is my x-intercept. The log of 1 is 0. Is this thing odd or even? It's neither. So there's no symmetries at all. What's the long-term behaviour? What happens as x goes towards infinity? Think about it. The log of 1 is 0. The log of 10, what power must 10 be raised to give 10? 1. What power must 10 be raised to give 100? 2. What power must 10 be raised to give 1,000? 3. So as x gets bigger and bigger, so does the log get bigger and bigger. It just gets bigger slowly. So in here, f does in fact go off to infinity. But I'll put in here, but slowly. That's not mathematical, the but slowly bit. That's just me commenting in there. And I guess the other thing is, this x greater than 0 says that x equal to 0 will be an asymptote. So I need to have a look at my asymptote thing. So what happens as x gets close to 0 from the right-hand side, as I come down here? So, for example, what's the value of when x is equal to 1/10? what power must 10 be raised to give me 10 to the minus 1? And the answer is minus 1. So 1/10 would be here. 1/100th would be minus 2, and so forth. So what's happening, as x goes towards 0, f goes towards minus infinity. And so this graph comes up like this. Now, to give you an idea of how slowly it gets large, this thing only reaches 1 when x is equal to 10. So it's out here like this, it goes like that. It is getting bigger, just really, really slowly. So that would be my graph of, whoops, wrong one, log x to the base 10. Looks like that. As I said, we're going to revisit this next week. So this is just our first look at it. When we had our exponential function, we found that to work with the exponential function, we needed to know our index laws. Now that we've got a logarithmic function, we're going to have a whole lot of logarithmic laws that we are able to use. All of the log laws follow from the index laws, in fact. So we can use all of these laws to do arithmetic and to do algebra with logarithms. So let me just put in here, these are important. Isn't everything? The first two are reasonably obvious, I think. b raised to the power always gives 1 no matter what b is. b raised to the power 1 always gives b no matter what b is. But this one here is not so obvious. It says the log of x plus the log of y is the same as the log of x times y. That's not all that obvious, but let me try to show you it. So let's look at this one. So let me go log bx plus log by is equal to log x times y. So the sum of the logs is the log of the product, I guess, is the way I would say that. So where does this come from? I can say this. Let's start off. Let b to the m equal x. Let b to the n equal y. And I guess the other thing I might do is let b to the m plus n be some number p. So I'm just saying, I don't know what those m and n's are, but it's the value that when I raise b to that base I get x, and so on. Now, from our index laws, we have p is b to the m plus n. That is b to the m times b to the n. That's one of our laws of indices, yes? B to the m is just x, b to the n is just y. So, using these relationships here, I can say p is x times y. Okay. Now, so if p is equal to x times y, then the log of p is equal to the log of x times y. P is b to the m plus n. What power must b be raised to give b raised to the power m plus n? Just m plus n. So on the left-hand side here I have m plus n. And I can say here, but I can say from up here, I can say the log of b to the m is equal to the log of x. So that tells me that m is in fact log b of x. Likewise, I can go for b to the n is equal to log by. So n is log by. And so out of all of that, I have here on the left log bx plus log by is equal to the log of bxy. Now, before you panic and start chastising me, I'm not expecting you to be able to reproduce such things. What I'm expecting you to say is, yes, it seems reasonable. He's been able to show me that this log law has followed from this particular law of indices. Okay? So all of these are logically following from the laws of indices. That's all you need to know. All right. So I shall leave that highlighted and I'll hide that bit down the bottom lest you have a heart attack. Okay. Let's use some of these. We're going to use these even more next week, but for the moment we'll just do a couple of simple ones. I think if you stare at that for long enough, you'll see that it does make sense. So, for example, here in Part A, it says you can use these log laws when doing arithmetic or algebra with logarithms. So, for example, here in A, log to the base 10 of 5/3. Now, if I could get my calculator out and I could just do that straight away. And what would I get? 0.2218 to 4 decimal places. And I do that via a calculator. However, not that it's any simpler, but just to show that it's equivalent, I could have also said that the log of 10 of 5/3, and I come over here and I use this law. The log of 5/3 is the log of 5 minus the log of 3. So I can write this one as the log of 5 minus the log of 3. Now, as I say, it doesn't get you anywhere in this particular example, but it is equivalent. And so if I were to work these out on my calculator, I get something like 0.6987 and a whole pack of things besides, and 0.47. Can't even read my own writing there. I think it's 2. 1, 2. But when I subtract those, I get to 4 decimal places, 0.2218. So when doing arithmetic, sometimes it's simpler doing this, sometimes it's not. But it's certainly handy to be able to rearrange these sorts of things when you're doing algebra, to simplify your algebraic expressions. So let me do one just with a little bit of algebra in here. So it says, write this thing. I haven't even specified the base, but I shall put it as base 10 plus 2 log 10x. Now, I want to simplify that. I'd love to be able to use log a plus, or log x plus log y is the same as log of x times y, but this thing's got a coefficient sitting in front of it, so I can't use that law to begin with, but I can use this law here to start off with. So I'm going to use that one to start with. 2 log x is the same as log of x squared. That's what I'm going to use there first. So this is going to be log 10 of 3x plus log 10 of x squared. That's my first law. Now I have a log and a log to the same base, and so now I can come back and use this one. The log of x plus the log of y is the log of x times y. So I'll now use that law, and this will become the log of 3x times x squared, which is the log of 3x cubed. And so there I've written that log as a single logarithm. Is that simpler than that? Don't know, but they're certainly equivalent.